just yet. So as you can see, we're not too far away from the end. Today we're going to do 7 and 8. I'm not here tomorrow. Friday we have 2 physics. So that would be 9 and 10. And then on Monday, is it? Tuesday, we'll finish. Now, sometimes I make this topic 2 lessons because of its importance, its usefulness, and so on. We'll see how we get on. But anyways, the first lesson first. You had breakfast? I know he has breakfast.
No.
Oh, that's terrible.
Sprite.
That's not a breakfast. Monica tried my porridge and you liked it, I hope. I like your thinking. I totally agree with this. Okay, here we go. Alright, so, RC circuits and graphs. No! The wrong bag!
It's expensive.
Look, what's that symbol there?
No, they told me this!
No!
I didn't even pick. I didn't even send me here. And then they are like, that one.
Back you go!
I have some present for you though.
What? Did they put that in? Those guys. Wait. Thank you. You don't mind going back?
No.
Okay. Who gave you this? Dennis or Isabel?
That is what they told me to say corner.
Okay. Thank you, Lee. I appreciate this. You're such a kind person.
I know.
Wait, Lee. Do you want some? Did you have breakfast?
Yeah, I did.
You don't want this?
No.
Are you sure?
Yeah.
It's delicious.
Okay, I will take that then.
Okay. Exactly the wrong bag. Not his fault though, the other teachers. Okay. Did you write that down? Yep. Did you get that, Andrew? Okay. So, the capacitor is fully charged up, like in a flash camera, and then it suddenly discharges. So the capacitor charges up, and then the energy comes out. Through a resistor. In the case of a camera, the resistor is the light bulb. I don't need to draw this because I don't have a pen, but you know what it looks like. So you have a capacitor and a bulb. That's it. But what I'm going to do now, this simple circuit has only 2 things in it: a capacitor and a resistor. So these circuits are actually called RC circuits, and you can see why, because I have it highlighted there: resistor and capacitor. So a resistor and a capacitor circuit is just a simple circuit that has 1 resistor and 1 capacitor, and that's all. And I'd like you actually to make note of that. So if you can draw a resistor capacitor circuit and title it as an RC circuit. Yeah.
Shouldn't we wait to leave?
I won't go past this slide if too much happens. Anyways, maybe a good teacher would wait for leave. I don't see anybody jumping to counter this. Okay, did you draw that? Now I'd like you to draw the circuit as well. One resistor and one capacitor, please. Okay, can I see it, Andrew? Correct? KJ, can I see?
One resistor.
One resistor, one capacitor. Okay. Chrissy, can I see? Did you draw the circuit? One resistor and one capacitor? Huh? Did you draw?
I wrote it.
Okay, but can you draw it as well, the circuit? Just one resistor, one capacitor. Can I see? Where the heck is it? Can't see. I'll have to trust you. Precious is a mistake. Okay, so now we'll add an ammeter to the circuit. It doesn't really matter where we add the ammeter. Can you add an ammeter to the circuit? You can put it, you know, after the capacitor or something like that. Chew, you're not writing anything.
Yeah.
Should write something, I hope. Okay, you've drawn that? So we added in an ammeter and we measured the current. Now what do you notice is happening to the current in milliamps here? As the time increases, what happens to the current? But of course that makes sense. What's happening to the capacitor? It's discharging, isn't it? So it should be decreasing. Now how it's decreasing is interesting. And the only way we can see how it's decreasing is if we graph this. So the next thing we want to do is make a graph of this. So I'll give you a minute. I'd like you to make the graph reasonably accurate. Yeah. If you could use a ruler at least. Yeah. Not what I had in mind, but
Do we have the graph paper in Excel?
of course.
You brought another surprise for you. Thank you.
Don't worry, I always carry one spare in my bag. Thank you very much, Lee. To recap what you missed, we have a circuit that has one resistor and one capacitor, and we call these circuits an OR-C circuit, standing for a resistor and a capacitor. And what we're doing is we're going to let the capacitor discharge and we're measuring its current. Now what do you notice is happening to the current as the time increases? Yeah, which of course is what you would expect a capacitor to do. But what I've asked everyone to do now is to graph this, to see what shape of the graph we got here. Did you make the graph, Chu? You see the pattern that's emerging, yeah? Has anybody, not yet, okay. Oh, Chew. What type of graph is that? I don't think it'll be a straight line. Yeah. You thought it will be straight? Yeah. You were trying to take a shortcut. Can you just connect the points and then show me your graph, please? Let's have a look. Nice. Okay. Andrew?
Do process.
Processing. Loading. It's like a curve. It is a curve, yeah. Okay, let me make it exact here. So maybe Andrew, you can just give me the data. The first thing is the time in seconds, and then the second thing is the current in milliamps. Right, we start at 0, and we increase the time until what? Until 10. Okay, and what's the first current?
100.
100.
50. 25.
Hold on, dude, hold on. Is this the second one? No, the second one's 50, is it? What's the second time? 70.7, yeah, okay. Alright. 70.7. Okay, so that's one decimal place. Alright, and then this goes all the way down until 3.1 about? Okay, that's two decimal places. I'd like this. Right, let's see the graph, exactly what we get here. Insert chart. Now you'll need to make these charts in your report, so maybe it's good practice to see this a couple of times. What graph type do I usually use here? No, actually it's scatter. I don't like this legend here. This is current against time. The x-axis is time in seconds, and the y-axis is current in milliamps. And you all should have a graph that looks like this. In fact, you might recognize this graph from maths class. If I zoom out a bit. If you look at your graph, what does it remind you of? What shape? Where have you seen this before?
Exponential.
Yeah, exponential. There we go. Exponentially decreasing. Oh, Sean, come on. What happened to you? What happened? Is the traffic bad, or was Sean sleepy?
No. I get up early.
You got up early and you were late.
Early.
You woke up early, but you were late.
Traffic is bad.
Should I trust you?
Yeah, of course.
Okay. Maybe I'll trust you. Right. Continuing. So as you can see, this graph is exponentially decreasing, which is maybe not a surprise because we picture the capacitor discharging quickly. So we assume that the graph is of this particular form. What I mean by that is we'll say that the graph, the current I, is equal to some constant we call I0, but actually you can kind of guess what the I0 represents. What would the I0 represent? The initial current, yeah. And then we have minus a t for time in seconds divided by a tau. This is a Greek letter, and this is called a time constant. Now, I need to put the minus in here. I must put this minus in. Why must I put the minus in? Well, if you think about our maths lesson, the minus is necessary for the shape to be like this. And of course, if it was positive, it's not what we want. It would be like this. Yeah. Okay. So we must have a minus here. This is called the time constant, and this is the initial current. Initial current. But there is a bit of a problem using this graph. What's the problem with graphs like this? Well, the problem with graphs like this is we can't actually see from the graph what the A and the B is. Okay, we can kind of see what the A is because the graph is going like this. So I could see the A here, right? But I can't see the B. It's not clear exactly what number value to use. So in physics, graphs that are curved aren't so helpful. They don't give us information. But graphs like this are much more helpful because we can easily see the M and the C. So basically our next job is how could we change that graph into a graph like this? That's what we'll be thinking about next. So just before I go on, this is kind of a useful notes I made, so if you can write this down. So the next thing is, can this be changed to a linear graph? We're missing Bruce and Jerry. Okay, continue? Yeah. So what the heck is the 1 over tau, the 1 over time constant? It's a bit like the K in our formula. Okay, so let's have a look at the graph. If instead of plotting the current, what about if we make a bit of a change? What about if instead, can I change this text, or there we go. So instead of plotting the current, what about if I plot the log of the current? Let's see what happens here. Now I want to change these all to logs. Log. Okay, so this one here would be I need to temporarily just put it down here. Equals log of this thing. Okay. How many values is that? 1, 2, 3, 4. Just replace them. Hold on, I know what I did wrong. I want to paste the numbers only. There we go. Now, and let's just do this to, no, too late now. Okay. If I was to calculate the log of the current and plot the log, what has happened to my graph? Now it's a straight line. So by plotting log current against time, I get a straight line graph. So,
why is it linear?
that's what we're going to look at now. Why? So, I've just done that. Notice how the graph is now linear. So, a very common question in the exam I've seen, well, sorry, that's not to say it's very common, but I've seen it in the exam. Sometimes what they do in the exam is they give you this table with the first two rows, and then the question would say, extend the table in a suitable manner. What this means is, add an extra row to the table, but they don't tell you what the extra row is. You need to know that for these problems, the extra row is a log of the data, of the current. And this is a trick, not a trick, but it's done on purpose in the exam. The question would be too easy if they just said, take the log of the data. I mean, any idiot with a calculator can do that. Instead, they make it a little bit harder by saying, extend the table in a suitable way. They don't tell you what the suitable way is. So you need to remember it's log. Log ln, basically. So, you have the table, I hope. If you don't have the table, I want you to write this, add this to your table. If you don't have the table, you should write this down. Have you done reaction rate in chemistry? No. So language check, I shall pick on Andrew. How might this question be stated in the exam? In other words, how might they ask you to get the log of this row, but without using the word log?
They will ask if a suitable way to plot a linear.
Half right. You have to give something suitable, but they won't say linear, they won't say log. They'll say give a suitable extension to the table. Extension meaning extra row, extra information. Okay, can I continue? Yeah. So, as KJ was asking, why did it become linear? And there are three proofs on the exam. 2 of them in semester 1 and 1 of them in semester 2. We've already done one of the proofs that could be on the exam. That is proving the UVATS formulas. This could be on the exam. However, it has never been on the exam. There has been about 40 exams, 30 to 40 exams in total. It's never been on one of them. I don't think it will be on any of the exams because the proof is kind of long. Could be on the exam. But that was the first proof that you could have on the exam. The second proof is what I'm about to do. And the third proof for the exam is in the next semester. So before you write down what I'm about to write down, make a note. This is possibly on the exam. And of the 3 proofs, this one and the next one is asked about, I'd say 25% of the time on the exam. So you have a chance, a reasonable chance that they might ask you to prove this. The proof is not very difficult, which is good. It uses what you learned in maths class. So let's have a look at the proof now. So we have the formula I equals I0 E minus T over tau. Sorry, I didn't realise you can't see it off the top. Now, what I'll do next, I'll apply a log to both sides. So now I get log I equals log I0 plus log E minus T over time constant. This was using the first rule of logs. Using the fourth rule of logs, I can change this into this. But let's just remember exactly what the ln means. The ln is actually, if I'm more precise here, this is log base E of E. Now what is log E?
1.
It's 1. So in fact, I can drop this. So I get log I equals minus T over tau plus log I0. Or, in other words, log I equals minus 1 over time constant T plus log I0. Now, if I'm going to make a graph, the graph I made earlier, what did I put on the x-axis? I put time. Yeah, and what did I put on the y-axis? I put log I. So this is actually y, and this here is actually x. So you can actually, if you look closely, you can see, oh, this is actually just a straight line relationship, because this is like an M and this is like a C. So therefore linear, or rather I should say, therefore log I against T is linear. This proof is on the exam. I've seen it a few times. It's one of 3 proofs on the exam. This is proof number 2 of 3. Now, if I'm being technical, there's actually more than 3 proofs on the exam. There's like about 6 proofs. But the other proofs are actually the same as this one. Because what will happen is, a few times in physics, we'll have formulas that look like this. And the question in the exam will be, prove that this formula can be written in a linear way. So, okay, I did say this is the second proof, but this actually, you see this in different parts of the course. For people who have studied radiation and half-life and alpha, beta, gamma decay, you'll see this proof again. The only difference is, instead of I, it's a different variable. Instead of tau, it's a different variable. The proof is the same though. Okay? So please write this down carefully. It's the second of your 3 proofs. And this is the most common of the 3 proofs, I would say, which is good because it's actually kind of the easiest of the 3 proofs. It's not too difficult. Continue. So, the verb here is linearizing. So when I linearize, I ended up with this result, which you already wrote down. And so, the important conclusion, or consequence, is that if log I is y, and x is t, then the slope is this, minus 1 over time constant. And the c is log I 0. And the c is log I 0. But in fact, this result here is very important. The fact that the m is equal to minus 1 over the time constant is really useful, because it means if I know the slope, I can know the time constant. So now I can get this result. Time constant is minus 1 over m. And that's how I can work out what this guy is. I think I put that in a box. No, I didn't. Or maybe I put it in later. So that's important. You can just make note of that. The time constant is minus 1 over the slope. Is the slope positive or negative? Negative. So is the time constant positive or negative? Positive then. Okay. Continue. But it's not just current which behaves like this. In fact, and we get this result. In fact, it's also true for the voltage and the charge. So the total charge that has been released is equal to Q equals, the charge left in the capacitor, how much charge it has, is also this formula, except the only difference is what? Well, instead of I0, it's a Q0. The same deal for the voltage as well. The voltage also has the same formula, except instead of I0 or Q0, at the beginning is V0. So you might want to make some note that these formulas are true for I, Q and V. Got that? Continue? Well, it's the same slide. The T, the tau, is called the time constant, and we actually already said this. You can find it by using the formula minus 1 over the gradient, the slope. We wrote this down. But there is actually another way to find it, and I haven't given you this formula yet. But in fact, if you know how big the capacitor is, and if you know how big the resistor is, then you can find the time constant by using this formula. Time constant equals RC. Got that? Continue. Also note, one use of the time constant is it can tell you how long it takes the capacitor to discharge. So if the time constant is 2 seconds, then it means it will take 10 seconds for the capacitor to fully discharge. So the rule is about 5 time constants is the time needed to discharge the capacitor. This is an approximation, but it's quite accurate. No surprise, the units are seconds. Okay, did you write this down? Now, this is actually very useful, because what might happen in the exam is you might have to make a graph. From the graph, you can know the time constant. If you know the time constant and you know the resistor, then you could work out the capacitance, or for example, the other way around. Let's have a look at an example. So in this example, the current discharges from a capacitor, and that's measured and recorded every 10 milliseconds. The table shows the data from the ammeter. So as the time increases by 10 milliseconds, the current, as you can see, decreases from 1000 milliamps down to about 200 milliamps. First thing is to make a graph. Okay, so I'll do this question with you. To begin with, I just need you to copy this table down, and I'll make the graph. So if you could just copy this table down. Okay, you got that table? Got the table?
No.
Here, are we just waiting for Sean? Yeah, we're all waiting for you, Sean. Okay. So let me just copy it here. I already have this open. Right, so the difference is this time is in milliseconds. And is it going up in tens, is it? Until what time?
100.
Cool. The current is in milliamps again, and it starts at 1000. Is the next one 840? Okay. I'll round this off to no decimal places. Okay, so if I graph time, you can't run that. What a small t. Okay. Is this graph right or wrong for the first part? Graph this. Is it right or wrong? Well, it's wrong because we shouldn't be using current. We should graph log of the current. Yeah. So let's change these into logs. Okay, so making these logs. Now, do I have this graph in an appropriate manner? Yeah, because now it's a nice straight line. In fact, let me draw the line in for you. Okay, come on, dudes. Dude. Insert. No. What the heck? Hang on, I can do this. Maybe just this? Can we imagine a straight line? We can imagine a straight line. Okay, can you just make a copy of this graph? Oh, what's wrong with my graph? My unit here is wrong. What did we say the unit was? Milliseconds. So let me just fix that. Okay. Now I got it. Let's put in my line. Okay. Wonderful, wonderful. Now, can you copy this into your notebook? Don't worry about this. You don't need the equation just yet. Just if you can get the graph. Wow, what happened to you, Bruce? And Jerry, what happened to you? Oh, come on, guys. Really?
It's already 20. Therefore, I can
Okay. What time did you arrive at? 9:20. Jerry, Bruce, in future, if you come at 9:20, I'll let you in class, okay? But if you do it too many more times, I won't. Yeah. Well, he's not going to get attendance for the first class. Anyways, Jerry and Bruce are good. They will watch my video later. So it's okay.
You don't say some bad sentence.
I said a bad sentence to you? Not today. Not today. Yes. Oh yeah. Don't worry about being too exact, okay? And let's look at the next part now. Part B. Estimate the time constant. So what do I need from the graph to get the time constant? The slope. Okay, Andrew, you have your calculator. So the slope will be... Now, in the formula there's two minuses, so I don't care about the minuses, it'll be a plus. So Andrew, the slope is going to be this distance over this distance. So everybody, if we look carefully, what is this distance? That's about... Is that about 2? Can't quite tell. That's 5, 6, 7. That's about 2. It's about 2 over 100, roughly. It's about 2 over 100, roughly. So roughly, the m is about minus 2 over 100, which means the time constant is about 1 over this. So that's about 100 over 2, which is about 50. About. This is about minus 0.02. Now that's actually not too bad, because if we look at the true answer was minus 0.017. So it's, not too far away from my rough guess. But there is a problem. I need to be very, very careful. What am I not thinking about as I do this? What I'm not thinking about is the units. We're using milliseconds and milliamps. Maybe the time won't be seconds, maybe it'll be milliseconds. Or maybe it will be seconds because the millis cancel. How can we know what the unit for the time constant is? Well, we can check it. So you remember on the graph, the slope is this over this, right? So the unit will be the units for the delta y over the units for the delta x. So on the top that'll be, y2 minus y1 units over x2 minus x1 units. Now, what is the units for x2 and x1? What's on the x-axis? Milliseconds. So what will be the units here? ms. Okay, good. On the top we have log milliamps minus log milliamps. So what the heck is that? Well, if I make it a bit clearer here, this is like log I2 minus log I1. And you might think, oh, well, that's just going to be milliamps. Well, no, it's going to be log milliamps. What the heck is a log milliamp? Well, it's going to be log I2 over I1. We all agree that's the same thing. But then we realize it doesn't actually matter what the units are for I, because this inside piece will have no units. So in fact, on the top, there's no units, which means you're left with 1 over milliseconds. And since the time constant is minus 1 over m, it means the units will be milliseconds. So that's good to know. It's good to know for the time constant, the only thing that affects it is the unit for the time. We don't need to worry about the unit for the y. It doesn't affect it. So if I'm using milliseconds here, it means my answer is in milliseconds as well. So earlier, this time constant is 50 milliseconds. Okay. How long until the capacitor fully discharges? How long? Yeah, the time to discharge fully is 5 time constants. This is a rule. So that is 250 milliseconds. And finally, how big was the resistor? Okay, well, the only formula I have is time constant equals RC. So the resistor will be the time constant over the capacitance. Now, again, we have to be careful, because on the top I'm using milliseconds, and on the bottom, do we know the capacitor? We do. It's hidden in the question. Current against time for a 200 millifarad capacitor. So on the bottom I have millifarads. So in total I have seconds and farads. That actually makes an ohm, by the way. If I had something like milliseconds over farads, that would be milliohms. And if I had seconds over millifarads, that would be ohm over milli, which is actually kilo ohms. Because 1 over milli is 1 over 10 to the minus 3, which is 10 to the 3, which is kilo. So just be careful with those units. So this is going to be in ohms. This will be 50 over 200 which is 0.25 ohms, which is 250 milliohms. That's the answer for that one there. So this question is largely a graphing question. Go ahead, Joe.
Can you
Zoom out. This much. It's a bit messy. This was part. What was part? Part C was how long? So sorry. This is part C. This is part D. These and this was just some notes I made about the units, and this was part B. Sorry about that. What's wrong?
No, we are finding the value for C.
As you wish. But I know the value for C. It's log 1,000. Oh, where's the value of C in the question?
Above the table.
Are you asking me something or?
Yeah, that one.
Okay. Happy children?
Yes,
I'm a mean father. Continue? Well, I think actually just to make sure that was the only. Oh no, I hadn't. No, that was not the example. That was the question here. Okay, let me give you this while you're writing that down. Give those behind you. Yeah. And that. Okay, and then this is for you three. Can I close this?
No,
1 sec. Lee, do you want porridge? I can put hot water in that.
No? Yeah, sure, thank you.
Yeah? Throw it. Okay. Have you got a spoon?
No.
Okay. You want porridge? Why? What did you do for me today? You did nothing. He went twice to get me a bag.
It's okay, we can share.
Well, continue working on these. I shall get the porridge. Can I close this?